So I welcome all the participants to the fourth day of this 1 week online faculty development program on new approaches in geotechnical earthquake engineering. I hope I'm audible to the participants. Very good morning to Tarun sir. We have Dr. Tarun Kumar Rajak with us today for the first session, and he is Assistant Professor and Head Department of Civil Engineering, Sri Shankaracharya Institute of Professional Management and Technology, Raipur. He has been former Assistant Professor and Head in Raipur Institute of Technology, Raipur from August 2020 to February 2021. Dr. Tarun Kumar has completed his graduation with honors and post-graduation in geotechnical specialization from National Institute of Technology, Agartala with distinction. He has successfully completed his doctorate in 2020 from NIT Raipur on topic stability of coal mine overburden dump material stabilized with industrial byproduct. He has also published 13 reputed papers in journals and conferences. And to his credit, he has one published patent also. We welcome you, sir, on behalf of the Civil Engineering Department at IPS Academy, Institute of Engineering Sciences, Indore. We are glad and honored to have you with us today, sir. And I request you to please take over the session, sir. Sir, your mic is on mute, and I hope the sharing option is active at your screen now.
Hello,
Yes, sir, you're audible.
sir. Hello, am I audible, ma'am?
Yes, sir.
Whether screen is visible, ma'am? Hello.
Yes, sir, it's visible, sir.
Okay, thank you very much. And
Sir,
now,
I
first of
request
all,
you. Yes, sir. Yes, it's visible clear now.
okay, thank you very much, ma'am. And first of all, I would like to thank the organizing team and head civil engineering department, IPS Academy, for conducting such a wonderful online FDP. And I'm Dr. Tarun Kumar Rajak, Assistant Professor and Head Civil Engineering Department, SSIPMT Raipur. And I'm here to present my research work on stability analysis of mine dump mixed with industrial byproducts. And during this research work, we have also got several consultancy works on this real field problem that I'm going to discuss here. So uh, I think I should start now. So moving to the introduction, basically what is the basic problem associated with the coal mine dump material and along with the how we can utilize some industrial byproducts at that field, and this is going to be discussed in this particular project work. And moving to the introduction, as you all aware that during the mining process, and it is the one of the important process and vital act for the production of huge economical minerals, and during this process the huge amount of overburden materials are generated. From this figure you can clearly see that during the process or extraction of the coal from the coal mine site, in case of open cast mining, we have to first remove the overburden materials or the soil which is present at that location. So this material has to be dumped in some convenient place, and as per the report of coal provisional statistics, government of India, Ministry of Coal, you can see that during 2019 for the removal of 632 million ton from all the coal mines of the India, they have to remove around 1,753 million meter cube of OB material. So what are the place we are going to be going to place this OB material? So basically there are two places we can dump this material. One is called internal dump. Whenever we dump this material in case of the mine site, it is called backfill. Or if you want to dump this over material or the mine is spoiled away from the mine site, it is called the external dump. So in all the cases, the stability of this dump has been a major concern over the years. And looking as I am living at the Chhattisgarh state, it has the around 16% of the total coal deposit of India, and it ranks second in the coal production by contributing around 18% of the total coal production all over the India. So these are the location map and the mineral map of the Chhattisgarh. You can see that there are different regions of the coal mines available in our state. So whenever we are dumping the mine soil or the overwood material or the mine soil, the failure of this dump may be caused by the downward movement of this material, and which actually results in the several losses of life, machineries, and sometimes it also halt the mining operation. Means we cannot go for the further production of the coal or the mineral ores from the particular location. So there are several factors which affect the stability of the dump. From this figure, you can clearly observe that one dumper and one machines are actually present there to dump this mine soil in the mine site. And this is how the slopes are formed in the case of dumping of the material in the mine site. So there are several factors which basically affect this stability of this type of slope, or you can say that is the mine dump. And there are some geological factors, means what are the foundation material are available there, what are the lithological profile, what are the ground profile, the soil formation, layering. These are the main factors which affect the stability. And the geometrical factors, you can clearly observe how the geometries are forming due to the dumping of this material, like dump height, like slope angle. And another one is the physico-mechanical properties. This is one of the important parameters which actually affects the stability of dump, which because it provides the stability of the particular materials, like cohesion, angle of internal friction, and density. These are the three parameters which actually provides the shear strength parameters to the material. Now fourth one is the hydraulic factors, which actually affected by the groundwater profile, or either due to the rainwater, either due to the saturation of the soil mass. These are the main four parameters which actually affects the stability of particular dump at the mine site. So whenever there is a inappropriate configuration of any of the four parameters, there may be the chances of dump failure. So these cases have to be investigated properly before dumping of material in the particular mine site. And these materials, from the figure you can clearly see, these are the material which is basically going to be used for the mine hole road construction as a pavement material. So this material should have a adequate strength to resist the upcoming stresses of the haul vehicles, the moving vehicles, which is like you can see in the Chhattisgarh region, there are the dumper of 40 millimeter cube of tons of capacity. The vehicle capacity is very high, so that this the stresses coming to the heavy vehicles is very high. So these materials should have a adequate strength. So so what are the basically motivations of the present studies, that during these mine dump failure cases, there you can see that several consequences due to the losses of lives. Like in the 1966, there are 144 persons were died, and in and after that in 1972 in USA, around 118 peoples were died due to the overtopping of the waste impoundments. So these are the cases of other from India, but still in India also from the 1956 continuously this dump failure is occurring in the mine site, which causes several losses of lives and machineries. From this figure you can see that this is the first picture of the Lalmatia coal mine of Jharkhand, where you can see that due to the failure of this dump material, how the machineries and equipments are damaged, and some persons were also injured, or some death had also occurred at this particular mindset. So these cases has to be investigated by the geotechnical engineers, and some appropriate solutions or remedial measures has to be given by all the engineers, the persons, for the safety and proper running of the mine site. So along with that, once we consume the coal in the thermal power plant, you can see that the huge bulk amount of the fly ash has been generated. In the Chhattisgarh region, around 28% of fly ash is still unutilized as per the report of Central Electricity Authority. And these are the scenario of the fly ash generation and utilization in the mine site. And these are the, as you all aware that these are the various modes of fly ash utilization. But in case of mine filling, in this figure you can see that only 4.65 percentage of fly has been utilized. So that's why we have gone for the particular problem, and that after the extraction of coal, we can also dump this fly ash and pond ash to get the maximum utilization and to achieve the full 100% utilization of the fly ash. Along with that, the GGBS, one of the another industrial byproducts which is widely used for the for the production of the cement, and this as per the research conducted by the Sarma at Sivapulya, they have reported that the combination of fly ash and GGBS, they both can be more beneficial than utilize them alone. So basically from all these studies and the particular field problem, we have decided our work to incorporate the some industrial byproducts, that is fly ash, pond ash, GGBS, along with the OB material or mine spile, to stabilize that material, to stabilize that slope, as well as for the construction of mine hole road. So these are the some methodology that we have adopted to conduct the several laboratory investigation along with the numerical modeling for the stability analysis of that mine dump. So and based on the numerical modeling, we have further suggested the optimum appropriate geometry and the what are the dumping sequence and the optimum amount of that industrial byproducts, that is fly ash, pond ash, along with or without addition of GGBS, that we can incorporate in our field and get the maximum utilization of the industrial byproducts. So this was the location map of the study area. We have collected the our mine dump material from the Gare Palma coal mine, which is the coal field of Man Raigad coal field and situated at the district of Raigad, Chhattisgarh, where we have collected our sample. From this figure, you can see the particle size of the OB material are ranging from 80 mm to the fine grained soil. These are the variations of the material which is present in the mine soil. So the proper investigation has to be carried out by considering the our limitations of the equipment, and based on that we have gone for the characterization of the material. So basically we have characterized our material by physical or geotechnical properties, chemical characterization, that is what are the elemental composition present there, and what are the microstructural the surface characterization that we have conducted. So these are the referred code for the experiments. And moving to the particle size distribution, it is the most important, because the particle size of the actual OB material was ranging from the fine grained soil to the around 80 mm, and so we don't have that much of laboratory equipment to investigate or to determine the geotechnical properties of that material. So how we can reduce that particle size? So there is a one technique called parallel gradation technique, which is proposed by the Love in 1964, that is used to how we can reduce the particle size and how we can somehow closely replicate the properties of the material, that is cohesion, angle of internal friction, how we can get in that available laboratory equipment. So that we have adopted that technique and prepared one model sample by reducing the particle size, but in that case the coefficient of curvature and coefficient of uniformity, that is Cu and Cc, should have remained same as per the native material. So we have prepared one model sample. These are the gradation of the model sample that we have prepared, and we are going to determine all the geotechnical properties based on this material, which is somehow closer to our actual or native material. And then fly ash, you can see that it is finer than OB material or the model sample. Then pond ash and GGBS, it is closer to the pond ash gradation. These are the gradation or particle size distribution curve of all the materials, And this is the compaction characteristics. Like from this figure you can clearly observe that the maximum density we are getting in the case of mine is file because it consists of rock fragment also, but fly ash and pond ash has the least maximum dry unit weight or dry density, and it has some significance also because of the lower unit weight. If you going to dump the material in the embankment, you will get the minimum stresses induced due to the self weight. So these are the basic important properties which are going to be beneficial when we incorporate the fly ash and pond ash in case of OB material. And GGBS we are getting around 18.5 kilonewton per meter cube of density. So these are the overall geotechnical characterization or the properties of all the materials. Moving to the gradation curve, we are getting that the OB material is well graded silty sand, and the fly ash is a finer particle. It is coming with the silt of intermediate compressibility, and a pond ash and GGBS are coming under the silty sand as per the USCS classification. And from this you are getting the very high value of CU value because we are prepared this model sample as per the native material, and these are the overall properties we have achieved from the materials. Now second one is chemical characterization using EDX test. So these are the elemental composition results. From this figure you can clearly observe that GGBS has the predominant content of calcium, and in the case of silica, yeah, fly ash, OB material pond ash, you can see that the silicon is predominant in that material. And as per also the report of Sharma and Sivapalia, they have stated that the combination of GGBS along with fly ash or pond ash can be more beneficial than utilize them alone. So based on that we have prepared these combinations to conduct the experiment. Now third one is surface characterization. You can clearly observe this figure that as you all have conducted the several tests on concrete, that fly ash is used to increase the workability because of the spherical shape. From this figure you can clearly observe the spherical shape in case of fly ash, and irregular shape are observed in the case of OB material and GGBS. It also provides the maximum resistance during the penetration in CBR, some out test you can observe. And in the pond ash you know that it is the combination of bottom ash and fly ash in the form of slurry, and here you can see that some hollow structure are also available, and some spherical shape is also available in the pond ash, which is giving the true picture of the spherical shape surface characterization by ACM test. Now these are the samples we have prepared by mixing different combination and considering the lower upper limit from the several literatures. We have prepared around 34 or 35 number of samples, and then different test has been conducted. These are the basic test you all aware, but as we are adding the GGBS in it, we are getting some cementitious matrix in that material, so that we have also conducted the test on the some curing periods also. The basic CBR test was conducted under 4 days of curing, but we have done it after certain amount of soaking period, like moist curing we have done, and this is how we have conducted several tests on that material. Now moving to the picture of compaction characteristics of that material. Now here you can see that with the addition of 10% fly ash, it is coming around 18.2. However, with further addition of 1 minute. However, with further addition of GGBS, you can see that the curve trends to left and upward direction. That means the dye density is increasing with the addition of GGBS from 6, 9 and 12%, and we are getting the lower moisture content. Similar trend was also observed if you added OB material with pond ash and GGBS. And these are the overall characteristics of dry density and optimum moisture content that we have got with the addition of fly ash and pond ash along with GGBS in case of minus file. Further, UCS test has been also conducted on the OB fly ash mix and OB pond ash mix without addition of the GGBS, because for the construction of mine hole road, as per the report of Tannat and Kumar, the material should have the capacity of 0.6 to 0.7 MPa for the gross vehicle weight of 4000 kilonewton. So we have conducted this test under various curing period also, like 7, 14 and 28 days. So these are the variations of UCS value for all the mixed proportion with fly ash combination and GGBS. Here you can see that the maximum value we are getting for the 12% of GGBS along with 10% of fly ash in case of mine is spoiled. So similar the variation in UCS value, you can see that for the black line wise for the 100% of OV material, that means the native materials, when we have added 12% of GGBS we are getting the maximum value. So how these variations are affected by the variations of fly ash, we can see that once we have added the 10% fly ash, the value gets shifted in upward direction. That means initially this finer particle, the earlier the OB material is comprises of sandy soil like some sand type of material, but if you added the fly ash it helps to fill the gap between the whites or the whites present in this particular mine soil, and that's why we are getting some higher amount of ECS. But up to certain limit, with further addition of fly ash, we are getting the reduction in UCS value due to the non-cohesive nature of the fly ash. This is how the variation in UCS value at different curing periods for OB fly ash and OB pond X mix we have got. Like in the blue line you are getting for the pond ash, again that value get reduced with the increase in the pond ash content. So now the CBR test also that we have conducted in the soak period, normal 4 days soaking as per the standard code, and further we have gone for the 7, 40 and 20 days curing, in which 4 days soaking period was constant, but initial days were considered as the moist curing. So during this period we have conducted this test, and for the mine hole road construction it was given in the guideline of the mine hole road design, it should have the CBR value of 25% at least. So test has been conducted. These are the soaked CBR value under the different combinations of fly ash and GGBS percentage. And from this value, we can see that at the 28 days of curing period, we are getting the maximum CBR value in case of OB material mixed with fly ash of 10% and GGBS of 12%. The similar UCS value that we are getting in the case of CBR value also. So these are the variations of the CBR at different curing period for OB fly ash and OB pond X mixed with 12%. We are only indicating the 12% GGBS. We are, because of that we are getting the maximum value. So these are the variation that we further increase of fly ash content from 10 to 40%. We are getting the reduction in CBR value. But as compared to the fly ash, the pond ash has the more frictional resistance. You all aware that the pond ash gives the more frictional value, phi value, as compared to the fly ash. This value get increased and we are getting slight higher value as compared to the fly ash in case of pond ash. So these are the test for UCS and CBR. Then further we have determined the cohesion, angle of internal friction, because which is required for the numerical modeling. So all the test we have conducted and determined the shear strength parameter. So this all the variations were reported here, that for all the mixed proportions what are the cohesion and angle of internal friction value we are getting. So these variations can be clearly observed in this figure, that for the native material, the cohesion value is coming around 20.46 kPa, and for 5 degree, the angle of internal friction is 31.10 degree. That what are the variations with the fly ash and pond ash, fly ash with the combination of cohesion, angle of internal friction value with variation of GGBS, we can see here that once we have added the 10% fly ash, the value of cohesion get increased. The similar the variation in UCS value, the C value is also varied as follows the similar trend. We are getting slight higher, that is coming around 28.2 kPa, and this trend got increased with the further addition of GGBS of 6, 9, 12%. And once we have added the 20% fly ash, this slight higher value we are getting. But again with further addition of fly ash, the value got reduced. And what about the phi, the angle of internal friction value? The fly values we are getting the low as compared to the native OB material. That's why it get reduced with the addition of fly ash, and the trend got continued with further addition of fly ash. But some variations we are getting in the pond ash, it doesn't follow the same trend. And once we have added the 10% of fly ash, definitely due to the non-cohesive nature of pond ash, we are getting some reduction in cohesion value, and this trend got continued with further addition of the pond ash. And once we have added the pond ash, what is the variation of angle of internal friction? Because pond ash has more frictional resistance as compared to the OB material, the value get increased, but with addition of GGBS we are getting the slight reduction. So the trend will follow the increasing value with the addition of pond ash. So these are the overall variation of cohesion as well as angle of internal friction value with addition of fly ash and pond ash along with GGBS. See, these are the overall summary, because in this figure we cannot understand in a single day that what are the variations we are getting for all the parameters, but overall summary I have presented here, that addition of GGBS in this OV fly ash, it causes the increase in MDD, but once we have added the fly ash and pond ash, we are getting the reduction in dry density, which is very much important in the case of numerical modeling. The mixed proportion containing 20% fly ash and 30% pond ash with 12% GGBS are showing the adequate CBR or UCS value. It is the resistance value. We are getting the adequate value, and that combination can be used for the preparation of material in subbase layer for the construction of mine hole road. So whatever the construction we are going for the road, that we can use for the subbase layer. The increase of fly ash content in OB material causes increase in cohesion and decrease in angle of internal friction. However, in case of pond ash, we are getting reduction in cohesion but increase in angle of internal friction. These are the two parameters that is varied due to the addition of fly ash and pond ash. Both are actually we got from the thermal power plant as industrial byproducts, but when we have added in the mine soil or the soil, we are getting somehow variation in this material. And the addition of GGBS in OB fly ash or OB pond ash mix causes increase in cohesion and decrease in angle of internal friction value. So these are the some way, comparison of our results with previous studies that they have conducted for mine hole road design. In the present studies, we are getting somehow to the 1 MPa or zero point 0.9 MPa, and as per the required value of greater than 0.7 MPa, we are getting this combination. First two combination we have proposed for our mine hole road design as a subbase layer. Again, for the CBR value comparisons, we are getting this again to this proportion, mixed proportions can be used for the mine hole road design. So these are our comparison of results with the previous studies. And then after getting all the results, I would like to say that after determining all the some basic parameters, we have to incorporate it in the numerical modeling for suggesting the optimum geometrical configuration of the mine dump that we have seen in the first 2-3 slides, that how the geometries are forming due to the dumping of material and how we can optimize the material geometry to get the maximum dump capacity. That means we can dump the maximum materials at that particular location with higher safety. So these are the combination as per the guideline of Director General of Safety and of Mines, that the slope angle should be varied from 28 degree, and based on that, based on analysis, we can get the optimum dump geometry. The dump height has been varied from 30 to 60 meter at 10-meter interval, and based on that we have suggested the optimum geometry. And further another sequence we have suggested that whether we should dump the native OB material from the toe level or the stabilized material from the toe level. These are the two variations of the dumping sequence we have conducted to achieve the height of 30 to 60 meter. And now in the particular Raigad mine that we have gone and collected the samples, the ultimate depth of mine was 120 meter. So for that we have also designed our dumping profile for the overall height of 120 meter, but in that case we have considered number of combination of decks, like benching we have proposed that you are going to see in the next slide. So these are the numerical modeling in the software, flex slope software, which is based on the finite difference method. In that we have simulated our geometry, and we have assigned several geotechnical parameters like cohesion, angle of internal friction, and density, which is based on the Mohr-Coulomb-Ferrer criteria. These materials model were assigned and the geometries has been varied to suggest the optimum dump profile. And this numerical modeling we have determined the factor of safety, and based on the limiting or the critical value of 1.30, we have suggested our optimum geometry for the various combination of mixed proportions. So these are the failure protein pattern of the dump slope. Here you can clearly observe that the circular slip surface is we are getting, and it is the most common failure pattern in the case of dump failure. In all the cases we are getting this circular failure pattern, and the variations of factor of safety has been determined along with the Serriston red contour, which indicates the low displacement of the material for the particular mine site. So these all the results we have observed from the numerical modeling of the particular mine dump. And these are the variations of factor of safety. This horizontal line indicates the limiting value of the or the minimum required factor of safety of 1.30 for the mine site, and based on that whatever the material which lies above this critical line can be suggested at the mixed proportion for the dump. And after getting the factor of safety, we have suggested the optimum dump geometry for mixed proportions. So these are the some basic summary that initially if you go for the native OB material or 100% of OB material, optimum dump slope we are getting around 30° for the 60 meter of dump height. But once we have added that 30% of fly ash utilization, it is very bulk quantity you can see in that mine site. Again you are getting the same profile, but if we added the pond s up to the 40% with or without addition of GGBS, we are getting slight increase in dump slope, which actually helps to increase the dump capacity. We can dump more material at the same OB material if we add the pond s. So another that we have considered the dumping sequence, like whether we should have to dump the native OB material first or the fly ash first. These are the combinations that we have considered for the dumping of material at the particular mine site for the particular layer thickness of h by 5, where h is the actual height of the dump, that is either 60 meter, from 30 to 60 meter we have added, and we have decided our thickness. So based on that, again we have suggested the optimum dump geometry. From this figure you can see that for all the cases we are getting the same dump profile. Because of mixing of material and layering of the native material, we are not getting that much increase in the optimum dump slope. But here we can say that we can utilize up to the 30% fly ash in that particular dump, because we can get the maximum capacity of fly ash at particular location. And also in the case of pond ash, we can also utilize up to the 30% pond ash at the same dump with same dump profile as the OB material. And hello,
Yes,
hello.
sir. Yes, sir. You are audible
Sorry
now.
for light got disconnected.
It's okay, sir.
It is visible, ma'am. Slides are visible.
Yes, sir. Slides are visible, sir.
Now for the overall dump height of that was the ultimate depth of the mine site, and it was around 120 meter. We have considered the several benching of the particular dump. That in the first case it was 4 deck of 30 meter individual height, 3 deck of 40 meter, and 2 deck of 60 meter. These are the combination we have considered. We have proposed for the particular location of the dump site, that we can bench and to get the further higher safety. So these are the overall optimum geometry. But you can see here how we are earlier we are getting around 30 to 32°, but in this case for the overall height of 120 meter, for the 4 deck of 30 meter each, we are getting around 40°. So this much of capacity we can achieve for the particular cases of the material with dumping with bench of benching of technique. So these are the variations we are getting on the stability analysis and the optimum profile, that for OB material 2 deck of 60 meter each, Earlier it was we are discussing over the 4 deck of 30 meter each, but for the maximum capacity we should go for the minimum number of benching, and for the 2 deck of 60 meter each we are getting 30 degree. Again for 30% flyers again it is 30 degree, but with 40% flyers pond days we are getting around 34 degree. Why we are getting this increase in optimum dump slope with addition of pond days? It is just because the pond days has the least unit weight and higher frictional resistance value. These two values actually beneficial for the increase in the factor of safety of the particular dump profile. So, as per the utilization of industrial byproducts, that is fly ash, pond ash, and GGBS, as per our current study and for the particular mine site of Gare Parma coal mine, Chhattisgarh, that we have conducted, we have found that in the mine hole road, we can utilize 70 million ton of fly ash. In the pond ash, we can go for the 105.6 million ton, and in the case of mine dump, you can see that for the fly ash we can go for the 105 million ton of fly ash utilization, and the pond ash we can achieve for the 140 million ton of pond ash we can utilize for the particular location of Gare Palma coal mine that we have studied. So the total quantity of OB material generation was 220 million meter cube at that particular coal site, where we can utilize this much amount of our industrial byproducts. These are the finding of the our research as per previous suggested geometry. And further, since we don't have that software's numerical modeling, so we have suggested some multiple linear regression as well as the artificial neural network modeling we have performed, and we have got one linear equation, and it is linear but we are getting very good regression statistics for the particular equation. We have run the data with 950 data sets and developed these equations, and we have validated also this equation with remaining 20% data, and the R square value is 95.0%, 7%. And similarly we have also developed the NN modeling, artificial neural network model we have performed and developed several architectures for that and suggested the best model. So these are the validation of the model. We have compared the predicted and observed value of factor of safety, and from this figure you can clearly observe that very close agreement between these parameters or these values we have found by developing this NN and MLR model. The values of R square is 0.99 and 0.94, and also after developing the our equation we have compared with some other researchers. So Seculario in 2005 has also proposed one equations and suggested to determine the factor of safety based on the several input parameters. We have considered the 5 basic input parameters, and based on that we have predicted the factor of safety with using our model, and we are getting around 94% of R square. However, the Caustic et al. We are getting the low prediction value just because they have also incorporated one another pore water pressure ratio RU value that they have also considered in that their equations. That is why by putting that value to 0 we are getting somehow lower value of R square. So another analysis, that is sensitivity analysis, that we have carried out to evaluate the sensitivity index and to keep the ranking of various input parameters, that is which is the most sensitive parameters or responsible parameters which basically affects the factor of safety or the stability of the coal mine dump. So Lenhart et al. Has proposed an equation. There are several sensitivity analysis techniques are also available, but this is one of the simplest method that proposed by Lenhart et al. That to determine the sensitivity index, and there is some remark or the sensitivity remark is also available based on this value, and for that we have considered all the 5 input parameters and conducted the sensitivity analysis, and then we have got the variations of factor of safety with respect to various input parameters and determined the sensitivity index I value. From this chart you can clearly see that the slope angle is most sensitive parameter and this sensitivity is very high, and is coming around 1.04. However, with respect to the other four parameters, you can see that all the amongst four parameters also high ranking comes under the high ranking. So whatever the five parameters we have considered in our study, we can see that it is coming under the severity of high to very high. So these are the oral conclusions that we have got from our study based on the UCS and severe characteristics for manhole road construction. These are the two mixed proportion, that is the material mixed with fly ash of 20% and 12% GGBS, or in case of pond ash you can utilize up to the 30% fly ash for the construction of manhole road. Based on the shear strength parameter and optimum geometry for the single deck, like for the 60-meter height, we can goes up to the 30-degree slope angle for utilization of 30% or 40% pondage with or without addition of GGBS. Or for the multiple deck of at overall height of 120-meter, we can say that we can goes up to the 30-degree or 34-degree in case of pondage for two deck of 60-meter each. And all the models were predicting the factor of safety with high statistical reliability with R square is greater than 9.0.90, and the sensitivity analysis also proposed that the slope angle is the most sensitive parameter, and all remaining parameters also come under the high sensitivity, and amongst that unit weight is the least sensitive parameter. So some research work we can also perform in that category by considering the hydraulic factors, that is we can simulate the rainfall in particular mine site, that we are again now we are working on it, that how we can simulate the rainfall on particular dump site and to determine the factor of safety or to determine the stability. We can also perform this analysis under the seismic loading conditions also, and some parameters that we have omitted from the present study, that is foundation materials like bench width, effective stress parameter. These other parameters can also be considered, and we can get the clear picture about the stability of mud dump or the mine site, how it is affecting due to the variation of these parameters. So these are the some publication based on that particular research work, and one patent we have also filed and it got published. Then how to prepare the composition and process of preparation of sub-base material for manhole road construction, and these are the details of conference papers. And thank you very much. So if you have any questions, please you can ask.
Thank you so much, sir, for a wonderful explanation. I request all the participants to, if you have any queries, you can raise it by unmuting yourself, or you can even type in the chat box. So that was a wonderful session, sir. Uh, we thank you on behalf of the Civil Engineering Department at IPS Academy, Institute of Engineering and Science, Indore, for taking out time from your busy schedule and enlightening us over the important topics that are related to this faculty development program. And we look forward to have your support and collaboration in future as well.
Thank you very much, ma'am.
Thank you so much, sir. So, in case if the participants have any questions raised, we shall definitely forward it to
Sure,
you.
ma'am, sure.
So, if you have any questions in the topic that sir is working, please get in touch with us. We will definitely forward your request to sir, and sir will be happy to address it at any time. Thank you so much, sir.
Thank you very much.
अभी इसके बाद मैम So we are taking a small break and we will be meeting at around 11:20 for the next session. And we request you to gather again at 11:20 for the session second of the today. So thank you for now. You can have a break for around half an hour.
Okay.